Welcome to ECE 203. This is a lecture on electrochemical biosensors. So far we've been discussing throughout this course, how do we measure electrophysiological parameters? These are things like biopotentials, ECG, EEG, EMG, and so on. But that's not the only thing that we can measure on the body. Certainly not the only thing we can measure non-invasively. There are other things that we could potentially measure on the body. There's physical parameters that we've discussed, motion through an accelerometer, respiration rate through strain sensors or impedance sensing, and so on. And while electrophysiology and physical parameters are very interesting, our body is a chemical system, right? And we would like to be able to measure these physiochemical properties as the body responds to treatment, as the body's undergoing exercise, or just during daily life. That would be really, really convenient. If we could do more frequent measurement of biochemistry, we would get a much better, clearer picture of the user's health status, either in general or for very specific diagnostic or monitoring applications. So if you want to do chemical sensing today, we draw blood. This is the basic way that we do it. Okay, so when you go to the doctor's office for, say, your annual health checkup, what do? They take your weight. They probably take your blood pressure, which of course is something that we would like to do in a wearable device, although that's a little bit more challenging. And then at the end of your appointment, they usually send you down to the lab to get some blood work done. And so what they do is they stick a needle in you, they draw some finite amount of blood, and then they take that blood, they ship it off to some diagnostic facility where they have these large machines that do the chemical analysis to figure out all sorts of various things, electrolyte concentration, small molecules, proteins, antibodies, antigens, whatever it is that you're looking for, they can test for it. But of course, this is not done very frequently. If you're a normal, healthy person, you at most probably get this done once a year. Probably many of us don't get it done once a year. It's only once every few years, right? So this is very much undersampling the response rate of the human body. In fact, the Nyquist rate, as we would know, is much faster than once per year. So we need to do better if we want to get a more comprehensive assessment of the user's health status. So one way to do this is through at-home testing kits. Okay, there are ways to do chemical analysis at home. A very common example is, for example, a pregnancy test. You can pee on this little strip, and depending on the symbols, it'll tell if you are pregnant or not. Another test is for diabetic patients. They have a problem generating sufficient insulin, and as a result, their blood sugar levels can spike after they eat a meal, and they need some way to control, or rather determine, how much their blood sugar is spiking so that they can appropriately inject the right amount of insulin. So the way that most diabetic patients do this is they have to draw blood. But they do this with an at-home testing kit, a glucometer, where you only draw a very small amount of blood, you place it near a little testing strip, and there's some electrochemical analysis, which we will learn about in this class today, that goes on that can determine how much glucose is in that sample of blood. A third example shown on this slide is a breathalyzer test. You can actually go on Amazon and buy a breathalyzer if you like. It's actually quite fun to bring to a party or something like this. But this is also an at-home test that gives you a spot measurement of, in this case, alcohol consumption. So these are what we would call point-of-care tools. These are devices that are used at the point of care, but it still only gives you a spot measurement. What we would love to be able to do is take, at least for some applications, take a continuous measurement. Perhaps that's not necessary for detecting something like pregnancy as an example, but it would be nice, certainly for someone who suffers from diabetes, they would sure like to know their glucose levels on a real-time basis. Then they can adjust their insulin levels or their intake of sugars appropriately. That would be really impactful. So here at UCSD, we've been doing a lot of research in general in this space. I'll talk about some of the applications perhaps later on in the lecture. But one application I did want to mention, at least up front, is we don't always have to do blood analysis. There are lots of physiochemical parameters that are well established in other fluids. For example, saliva is a good place to measure things like uric acid. This is something important for patients suffering from hyperuricemia or gout. And then there's also measurements of things like lactic acid or lactate, which, by the way, has nothing to do with milk. It's just it's a biomarker that indicates the exertion level of the patient. So some of the work that we've done somewhat recently, or I guess a little while ago now, was to measure real-time saliva constituents using an instrumented mouthguard platform. So we will, in this class, learn about how we implement the circuits that are used to do this kind of detection. There's other examples, for example, from industry. This is a project run by Google or Verily, whose objective was to try and measure glucose concentrations in tears. And the idea here is you could build a electrochemical sensor, put it right onto a contact lens. You could spiral some coils around the perimeter of this contact lens to do wireless power transfer and telemetry, which, by the way, is a topic we'll talk about in a later lecture in this course, and wirelessly read out the glucose data from your tears. So conceptually, this is a really cool project. Lots of really good technology needs to go into such a system to make it work. Unfortunately, it turns out that glucose in tears is not that well correlated to glucose in blood, and as a result, this project was canned basically by Google. So that's not to say we won't see in the future some sort of smart contact lens that does some sort of electrochemical analysis. Perhaps just glucose wasn't the right choice. So the future vision in wearable device technology, in my opinion anyways, is going to go towards devices that are, first of all, soft and stretchable or flexible, devices that can mate with the properties of human skin very nicely, and that can measure physical, electrophysiological, and physiochemical parameters. So I would like to spend just a minute talking about these form factors. This won't be really a big focus of our discussion in this area right now, with the exception of power consumption, which will hopefully be clear momentarily. But I'd like to talk about the vision for the form factors of these devices. What I'd really like to do in this case is take the human out of the loop. So if you look at current wearable devices today, the human has to be responsible for putting the wearable device on. And if it's just a smartwatch, this is not a big deal. But if it's a smart patch or something like this, you do need some specific user interaction to do so. And if the user doesn't place it correctly, or if they forget, or if they don't care anymore, you're not going to get the functionality of your wearable device anymore. So what I would like to see happen in the future is to take the human out of the loop. We want to build wearable devices that are so small or so unobtrusive that the user is virtually unaware that they're wearing their wearable. Okay, so I like to call this unawareables. Okay, these are devices that are integrated directly into the clothing, the glasses, the shoes, the underwear, the socks, the rings, everything that we all normally wear on a daily basis. We are integrating sensors into them such that the user doesn't have to change their behavior at all in order to get access to some rich wearable sensor data. If we can do something like this, and this is a research vision, we're not there yet, but if we can do something like this, this will be very powerful for our global community. So in order to get there, we of course need to continue to developing new sensor technologies. We'll talk about the physiochemical sensors today. And these devices need to be super small, super low power, ideally not operating with batteries, and there's a whole host of other challenges that we need to address here. But there's a lot of research topics that need to be sorted out here in order for this to happen in the future. So hopefully I've convinced you that it's a good idea to try to measure chemical parameters on the human body. We can do this in a number of different solutions. We can do it in blood, saliva, tears, urine, sweat, etc. Anywhere where there's fluid, we can typically try and measure some chemical parameters. But how do we do this, right? So how do we measure the concentration of glucose, right? Our electronics conduct information with electrons, and so we need some sort of way to transduce between, say, our glucose or small molecules and electrons. Now, we've talked a lot about in this course about ions. So maybe you have some notion in the back of your mind of how you might measure ion concentration, because we have kind of discussed how to transduce between ions to electrons through what we call electrodes. But how are we going to make these specific? How do we say we want to detect potassium ions only and not also sodium ions and any other ion that happens to be in that fluid? How are we going to do this? So these are really the challenges set up for when we try to build electrochemical biosensors. Is how do we get good selectivity? That is, how can we make sure that we're identifying sodium and not potassium? How can we get good sensitivity, making sure that we can detect very small quantities or very large quantities? We want to be able to satisfy the appropriate dynamic range. And then, how do we do this all at very low power? So it turns out that there's three main classes of electrochemical biosensors. Now you can measure chemical parameters not electrochemically. There's many other ways to do this optically and so on. In our case, we're going to focus on electrochemistry because it's a convenient way for us to measure. It also happens to give us pretty good specificity and sensitivity. And if you're careful about your circuit design, you can usually do this at quite low power. So there are three different ways to measure chemical properties using electrochemistry. There's potentiometric sensing, which is basically the measurement of an open circuit potential between two electrodes. And it usually gives a log of the concentration to voltage output relationship. This is typically used to measure things like electrolytes. There's also voltammetric ways to measure things. This is the measurement of voltage and current characteristics between two or sometimes three electrodes. A very popular subcategory of these type of sensors are amperometric sensors, where we keep the voltage on across the two or possibly three electrodes constant, and we read the resulting current out. This usually gives us a linear relationship with respect to the output. Now, this is usually useful for very high sensitivity across a small linear range. So if you have a very low concentration, this is something that typically works fairly well due to the linear relationship. And we'll study all of these in more detail. And the last one is conductometric. This is, as the name implies, the measurement of impedances across a sensor or at one or multiple frequencies. So what is electrochemistry? Well, hopefully you've studied at least a little bit in your high school and so on chemistry classes, but basically it involves the practice of converting chemical signals, either ions, small molecules, etc., into electrical activity. And this is primarily achieved through redox reactions. Redox reactions are a set of reactions which do this conversion of ions and so on into electrical activity. Oxidation, for example, is a process in which an element attains a more positive oxidation state. So, for example, we could go from sodium in the solid phase, this is what this S represents here, to a sodium ion in the aqueous phase. Oops, forget the U here, plus an electron. Okay, so this chemical reaction or electrochemical reaction allows us to convert from an element into something that has current flowing across it. Reduction is a process in which an element attains a more negative oxidation state. So for example here, we could go chloride plus 2 electrons gives us 2 chloride. So just to be clear here, this N here is the number of electrons transported per unit of reaction. So there's a nice old memory device for oxidation and reduction. It says Leo says Gur. Leo the lion says Gur. So Leo means lose electrons equals oxidation, and Gur means gain electrons equals reduction. So the key to understanding electrodes is the interface between the electrode and the solution. And it turns out that a potential will develop at any interface or junction, if you will, when there's a separation of charge. So a p-n junction can develop a potential when there's a separation of charge, if light hits it or whatever. A metal electrolyte interface will also do this. So if we take a piece of zinc, and we'll call it an electrode, and we place it into a solution of pure water, what's going to happen is that the piece of metal, this zinc, has a very high concentration of zinc atoms, right? Obviously, it's all zinc. Whereas the water has very low, in fact, zero concentration, at least initially, of zinc atoms. And so what's going to happen is that zinc atoms will dissolve into solution via a redox reaction shown below. But at the same time, what's going to happen is we're going to start to get positively charged ions accumulate in the solution. At the same time, we get a bunch of electrons accumulating on the piece of zinc, and this creates an electric field, which serves to drift the zinc ions back into the wire. So as you can imagine, this situation sounds pretty familiar to us. This is a classic Boltzmann setup, or Boltzmann distribution. So at equilibrium, drift and diffusion are equal to each other. And so just like we derive for the charged particles, or the particles in the Earth's atmosphere, or for charged ions across a cell, we can model this with a Boltzmann distribution. Alternatively, we can determine the potential developed across the electrode given by the Nernst equation. So we say that the voltage is equal to some reference voltage V0 minus RT over Z times F times the natural log of the concentration redox over reduction over oxidation, alternatively given by V0 divided by RT over ZF times the natural log of Q, which is what we would refer to as the reaction quotient. Okay, so if you go ahead and just stick this electrode in solution, we are going to develop, as measured by this expression here, what we call a half-cell potential. Now, we call this a half-cell potential because in order to measure a voltage or a potential difference, you need a potential difference. You need 2 points to measure a voltage. And if you just stick one electrode into solution, it's theoretically not possible to measure its voltage without also sticking another electrode into the solution, which would cause another electrochemical reaction to happen, at which point you're measuring kind of both of the electrochemical cells, if you will. But we can theoretically compute, based on the measurement of 2 cells, what the measurement of 1 cell or a half cell would look like. So in this case, we say that V0 is the potential when normalized to 1 molar of concentration at 1 atmosphere of pressure. So here's a table listing a bunch of standard reduction potentials at 25 degrees Celsius for 1 molar concentration. So what we tend to do is we need something to use as our reference. So in this case, we tend to use a standard hydrogen atom as our, a standard hydrogen electrode as our reference, and we define this to have a half-cell potential of 0. It doesn't actually necessarily have a half-cell potential of 0. It's just this is our definition of what it ought to be. And then what we do is we measure all of these other electrode types with respect to this standard hydrogen electrode. So this table lists all of these different potentials. You can see they vary somewhere between -3 volts to +3 volts or so, depending on the type of electrode. So let's take a look at two examples. Let's take a look at a silver electrode. We can go ahead and calculate what that Nernst potential is going to be for a silver electrode. V0 is just referenced to the standard hydrogen electrode, and then RT over ZF, these are fixed parameters. So what we say here is that it's equal to 0.8 plus 59 millivolt times the natural log of the reaction quotient. Okay, so basically what this means is that if we were to plot the voltage of this circuit at 1 molar of concentration, we would get V0 of a half cell potential, again with respect to the standard hydrogen electrode. And then as we go down from this 1 molar concentration, we're going to get some logarithmically declining slope here in units of, or with a slope of 59 millivolts per decade. That would be theoretical. This is what we would call the ideal case if we directly followed the Nernst equation. Now, in practice, in reality, it's hard to measure things all the way up to a molar of concentration just due to the way that the electrodes are built and so on. And so in reality, we get a pretty good approximation here, and then at some point we start to saturate out here. So this is reality. Now we can do a similar exercise for zinc. In this case, the half cell is minus 0.76 millivolts plus 28 millivolt per decade. So this is a steeper times the, sorry, not millivolt per decade, millivolt times the natural log of the reaction quotient. So this is a steeper slope here at 28 millivolts per decade. Of course, it will saturate out as well, but I think you get the idea. So this slide just summarizes what I was talking about earlier. What we were just talking about were half cells, and as I mentioned, it's impossible to measure directly the potential of a half cell because you need another electrode to make that measurement. And so an electrochemical cell we say is defined as containing two half cells. And we say that our half cell potentials are always measured with respect to that standard hydrogen electrode. So here's an example of a representative electrochemical cell. We see we have two electrodes here. They're both dipped into solution. The anode is where oxidation happens. The cathode is where reduction happens. And we have a salt bridge, or some sort of porous disk that allows ions to flow without, mixing the solutions, essentially. So this is our basic electrochemical cell that you probably studied when you were in high school or introductory chemistry classes. Let's take a look at an example. In particular, let's look back at that example for zinc. So we know zinc is going to undergo redox reactions until we reach equilibrium between drift and diffusion. But what if we did something external to the circuit? What if we allowed some pathway for the electrons to flow? If we allowed a pathway for the electrons to flow, then we could disrupt this equilibrium condition, and maybe we could get current to flow continuously. So, for example, what if within this zinc, or in this solution with zinc in it, what if we had another electrode of copper? We put that in solution as well. Well, it turns out copper has the opposite electrochemical reaction, where we can take copper ions plus electrons to generate solid copper. And so the electrons that are coming out of the zinc electrode could then just be directly recaptured by the copper electrode in order to create more solid copper, provided, of course, that there's enough copper ions in the solution. So as a result, we can basically combine these two half-cell electrodes in order to get something that has current that actually flows through it. So with that very, very basic refresher of basic electrochemistry, let's talk about how we would build these different types of electrochemical biosensors. And in particular, we'll start with potentiometric biosensors. So in potentiometric biosensors, we intentionally do not want a current to flow through the circuit. In fact, we want to measure effectively what amounts to be that half cell potential, that open circuit voltage. So in that case, how do we get specificity from our electrode? Well, what we need to do is we need to functionalize one of the electrodes such that only specific ions will change the half cell potential. We call this an ion selective electrode. So this measurement must be made with respect to some sort of reference, some other half cell. Typically, this is not implemented in practice with the standard hydrogen electrode because these are kind of, not easy to miniaturize and so on. But typically with respect to some other standard electrode like a silver-silver chloride electrode or, a number of other possibilities. So the idea here is we put these two electrodes in solution, our reference electrode and our ion selective electrode. And as the concentration of ions that is corresponding to this ion selective electrode changes, then we should be measuring a change in voltage. And that is how the circuit works. So sensitivity for this sort of circuit then is then determined by how accurately one can measure this potential difference. So here's one way you could conceptually make an ion selective electrode. You could take two of the same electrodes, let's just call them your reference electrodes. You put one of the reference electrodes directly in the solution, that would be this guy over here. And then you put the other one in kind of its own special little box that happens to have an ion selective membrane right at the bottom here. And so what this ion selective membrane does is it, as the name implies, selectively only allows specific types of ions to pass through it. So you could make this, sodium, potassium, hydrogen for pH, all sorts of different types of ion-sensitive membranes could be used here. And as these ions travel across this membrane, we're going to, in this case, adjust the internal concentration of the internal solution within this ion selective electrode, and that could be measured by measuring the open circuit potential between these two circuits. Now, as we mentioned, there's a linear range over which these types of devices operate correctly. So we have interference at the low detection limit from cations and interference at the high level of detection from anions. In addition, we say that no ion selective electrode is perfectly selective. That is, we make these membranes as good as possible, but they're not perfect. Okay, so if we make a hydrogen selective membrane, it's difficult to ensure that only hydrogen atoms, hydrogen ions, can pass across that membrane. It's likely that other ions will, occasionally make its way across the membrane. So as a result, what we can do is we can model the imperfect selectivity with something we call the selectivity coefficient. Okay, so normally the Nernst equation is governed by this piece here, where alpha I is this, reaction quotient, if you will. But what we can do here is we can say, well, ideally we respond only to alpha I, which is the ion in question. But if there's other ions in the solution, alpha sub j over, and there's many possible sub j's, then they will affect the resulting voltage readout, but they're going to do so with a sublinear relationship and with a selectivity coefficient that is not unity, ideally less than unity. So if it's significantly less than unity, then we can say that we have an electrode that is pretty selective. So we've gone ahead and built some of these in our own labs for wearable devices. This is some work done in collaboration with Joe Wang and Nanoengineering. And what we saw here is that if we build, say, for example, a sodium selective electrode, you can see here we get this nice linear response between a log varying sodium concentration and a linear output voltage. Okay, so this is actually exactly as we would expect from the Nernst equation. But let's say we've also built a pH sensor, okay, that responds to hydrogen atoms. Ideally, this shouldn't be affected by the concentration of sodium ions, right? If the sodium ion concentration changes, the pH sensor voltage should not change at all. But you can see here there is a little bit of change that goes on here. So what this means is that it's actually difficult to design a perfectly selective ion selective electrode. But this is not necessarily the end of the world. As long as these relationships are known, we can calibrate all of this stuff out. Okay, so we can dip our electrode into known solutions of sodium, pH, and so on. And by modeling what their selectivity coefficients are, as long as we have all of these sensors present in our eventual actual system, then we should be able to calibrate all this stuff out and still get a very accurate depiction or accurate assessment of what the underlying concentration of each ion is. So now that we have at least a minimum understanding of how these potentiometric sensors work using ion selective electrodes, what are the considerations to design the electronics? Well, they're actually pretty simple. We're just trying to measure an open circuit voltage. So, any high input impedance instrumentation amplifier will work just fine. The voltage range depends strongly on the ion selective electrode, but typically it's somewhere between 0 and 1 volt. Because this is the voltage range, we typically don't need or in fact want any gain unless we're trying to do very highly selective measurements over a very small concentration range. But typically, frankly, we have a gain of 1, 2, 5, maybe 10 at the most for these sort of systems. The input impedance should be large, right? We don't want current flowing through this circuit, so we want to make sure that we have a very large input impedance to make sure that we're truly measuring an open circuit voltage. This, of course, the requirement for the input impedance depends on the impedance of the electrode itself, but typically somewhere, north of 10 mega ohms is in the right ballpark here. In terms of bandwidths, if we're just trying to measure the concentration of, say, pH, sodium, potassium, and so on in sweat or saliva, this is not something that varies very quickly. Okay, so I'm going to say the bandwidth requirement is much less than 100 hertz. Probably something like 1 hertz is more than sufficient for these kind of measurement systems. Now, with that said, that's not the only place where we use ion selective electrodes. We could use them to measure the dynamic concentration of ions in a cell, and in that case we need a much larger frequency. So given those constraints, what would an actual ion sensing system look like using a ion selective electrode? Well, look perhaps something like this. This is one that we built in my lab here at UCSD, and the idea here is you take an ion selective electrode over here and you put it into a potentiometric amplifier, which is really just acting as a buffer in this case, because depending on the type of electrode, the voltage could vary, anywhere from 0 to about 1 volt. So we really don't want any gain, particularly if our supply voltage is not that high. In fact, in this particular work, our supply voltage was 0.6 volts, which ultimately sets the limit of the voltage range of the potentiometric amplifier. But for the types of ISEs that we were looking at, that was perfectly fine. Okay, so we take the output of the ISE, we buffer it, and then we put it into an analog to digital converter. In this particular case, it was a type of SAR analog to digital converter. And then we want to take that digital data now, serialize it, and do some pulse shaping. The pulse shaping is for the subsequent block, which is a 2.4 gigahertz wireless transmitter. This wireless transmitter will wirelessly deliver the sensed information, to some distal sensing point, a cell phone or something like this. This entire system was powered from a lithium-ion coin cell battery, which has a higher voltage than desired for the chip. So we have a 3-to-1 switch capacitor DC-DC converter that generates a lower supply voltage. We call this VDD, which is the 0.6 volts. And we have a clock circuit that's used to clock all these things. We even also have a reference electrode voltage generator, which is used to push a specific voltage onto this reference electrode so that the voltage measured at the ion selective electrode is in the right common mode, if you will, in order to make sure that we're in the proper input common mode range of the potentiometric amplifier. Now, what's really interesting about this particular work is that every single circuit here was optimized for extremely low power consumption. In fact, the entire power consumption on average when this circuit was operating, I believe it was at 10 samples per second, or roughly 5 hertz of bandwidth, which is more than sufficient for many ion sensing applications. The average power was 5.5 nanowatts. Okay, this is extraordinarily slow, and that includes that 2.4 gigahertz transmitter. The reason the average power is so low is because the data rate is low, right? This transmitter is not on very frequently. The peak power is in the hundreds of microwatt regime, but because we can duty cycle it, and we're very careful about how we do power gating to duty cycle that transmitter down, such that its standby current is in the low single-digit nanowatt range, we can make sure that the overall system power consumption here is extraordinarily low. So 5.5 nanowatts is actually lower than the self-discharge rate of most coin cell batteries. So most coin cell batteries have a self-discharge rate. The battery's just sitting there on the shelf, not connected to anything, and it's consuming about 10 nanowatts. So if we hook up our wireless ion sensing system here, it's consuming 5.5 nanowatts. That's within the ballpark of the battery self-discharge rate anyways. And so if that battery is spec'd to last for 10 years, then adding this circuit and your system will also still last for about 10 years. Okay. Now this is of course ignoring the fact that the ion selective electrode itself may not last for 10 years, but I think it's a nice step in the direction towards this concept of unwearables. If we really only need single-digit nanowatts to power our circuits, then we can get away with very small energy harvesters, very small batteries, and so on. That'll be more than sufficient for the needs of many of these emerging applications. So here's some system testing results. What we did is we took a measurement, and in fact you can see the picture of the electrode here, the ion selective electrode, and then the reference electrode below it. And what we would do here is we would step the concentration, in this case I believe it was of sodium, over time. And you can see here that over time the voltage on the ion selective electrode goes from about 500 millivolts to about 200 millivolts or so. And if you plot this on a log concentration domain, you'll see that we get a nice near Nernstian response. Now here's some work that was done by Professor Joe Wang's lab that showed that you can build these systems for sodium, and you can actually do real-time measurements. So these measurements down here are very similar to what we did with our chip. They were taken with larger and bulkier equipment, of course, but you can actually get some real-time measurements happening here, where you can start exercising, and as you start exercising, you start to sweat, and within your sweat are electrolytes like sodium, for example. This might be interesting to measure for new and emerging applications. So we were just focusing on potentiometric biosensors. I'd like to now shift our focus to amperometric biosensors. The idea here is instead of measuring this open circuit voltage in a potentiometric sensor, what we want to do with an amperometric biosensor is apply a voltage between the working electrode and the reference electrode and measure the resulting current. Now this is typically used to sense small molecules. These are typically of such a size and construction that they can't be easily selected by a semi-permeable membrane. Okay, so as a result, we have to get more into electrochemistry, and what we typically do here is we develop an enzymatic layer. Okay, so we functionalize the surface of the working electrode with a particular enzyme, which will interact with the small molecule that we're trying to sense and catalyze a reaction that will ultimately transfer electrons to our electrodes that we can then, of course, sense electronically. Now, it turns out that these enzymes are typically only active at particular voltages. So this is why we want to apply a very specific type of voltage to our electrochemical cell. And if we apply the right type of voltage, the cell will become electrochemically active. Current will ideally want to flow. And it turns out that the magnitude of current that flows is, in normal cases, proportional to the underlying concentration of the small molecule that we're trying to sense. In terms of specifications, this current range is normally in the, let's call it nanoamps to maybe microamps regime, depending on the size of the electrode and the enzyme and a host of other things. But it could go down all the way to femtoamps, or possibly as high as milliamps, although that's not as common. So a basic amperometric measurement system looks something like this. We have two electrodes. We dip them into solution. Again, solution could be sweat on your body, could be blood, could be urine, saliva, and so on. And we want to apply a very specific potential between the working electrode, which is functionalized with that enzymatic layer, and the reference electrode. So we do this with some sort of voltage source. And then we want to measure the current flowing through the circuit through, in this diagram shown as an ammeter. But there's a slight problem with doing this. We want to apply a specific voltage, but if we have current flowing through the circuit, this is going to cause IR drops. It's going to cause IR drops across solution, which is fine. It's going to cause IR drops across the electrode interfaces, okay? And this might cause the voltage difference between the working and the reference electrode to be less than the desired reference voltage, okay? And we don't want that to happen because we do want a very specific voltage operating across between the interface of the enzymes on the working electrode and the solution. We really want that to be a very specific voltage to make sure we're getting the proper amount of enzymatic activity. So one possible solution to this is to make the reference electrode really big. If the reference electrode is really big, its impedance is going to be low, and therefore the IR drop seen across the reference electrode is going to be very low, and as a result, the solution will be biased at very close to precisely the voltage of the reference electrode, and then we'll know exactly what the working electrode to solution voltage is. So this can and does work. However, it's not always practical in systems where we need to be small. We need to miniaturize the entire system. So for that perspective, we like to try and build, or we typically will build what we call a three-electrode amperometric system. Again, the desire here is we want to apply a very specific voltage between the reference electrode, between the working electrode and the solution resistance. The solution potential. The solution potential is set by the reference electrode. But the problem we had in the previous slide is that if there's current flowing in that reference electrode, then it could have an IR drop, and then so therefore the solution potential won't be what we expect. So the idea with a three-electrode amperometric system is to do the same thing. We apply some voltage between the working electrode and the reference electrode, as we normally want, but we don't allow any current to flow through the reference electrode. Okay, we make it look up into here some high impedance. Instead, we add a third electrode that allows current to flow through the cell from the working electrode to what we call this third electrode as the counter electrode. Now, in order to make this happen, we need some sort of circuit that sets the voltage between the working electrode and the counter electrode to precisely the right value to allow the current to flow naturally without inhibition. So normally when we need a very precise setting of a voltage, we don't typically want to do this through like an open loop driver or something like this. We typically want to do this through a feedback circuit. This feedback circuit that we typically use is what we call a potentiostat. So potentiostat at its most basic level looks something like this. Okay, so remember, we're trying to fix the voltage between the working and the reference electrode. So if you look at this circuit, the working electrode is on the bottom here. The reference electrode is over here. So if we ignore the counter electrode for just a moment, and let's say we have this op amp, and we set minus Vref to the positive terminal here, then if the op amp has infinite gain and is configured appropriately and in a stable manner, then this voltage on the negative terminal will also be equal to Vref, just simply through the feedback nature of the op amp. So the cell voltage, which is the working electrode minus the reference electrode, in this case is 0 minus Vref. So this is equal to Vref. So by using this potentiostat circuit, we are able to set the cell voltage to be precisely this reference voltage, which is what we're looking for. Now, the feedback circuit is critical here because not only is it being used to set Vref, it's also just so happens to set the voltage at the counter electrode to just the right value to allow the current to flow through the electrochemical cell correctly. Okay, so and this is this cell current here. It could be in either direction depending on the polarity of the system. So this is great. This actually works very well. We do have to be careful here because we're building a feedback circuit. And as we know, feedback circuits can have stability issues. So we have to be mindful of that when we're designing it. And to make matters worse is, we may not know the exact properties of the electrochemical cell. So as a result, we may not know what the stability is until we hook the cell up or at least characterize a particular cell. So that is something that we do need to be concerned about. Now there are, in terms of requirements for the potentiostat, we typically need that op amp to have fairly high gain, so we get very good precision on setting that reference voltage. We want it to have low input referred offset to make sure, again, that we have good precision on setting the electrochemical cell voltage. It needs to have fairly low noise. And it needs to have sufficient bandwidth in order to, operate over the types of cells that we could possibly have to make sure that the cells can stabilize in a reasonable amount of time and so on and so forth. So that was one particular way that we could have built a potentiostat. There are many other ways we could do it. All right. So in that particular case, if we have a CMOS as our input, that works perfectly fine. But if we have something like a BJT or something like this, then we might have some impedance problems. And so one way to resolve those impedance problems is to add some buffers, right? So you can have a first stage buffer here to make sure that this voltage is minus Vref. And then you can have another buffer over here to buffer out the reference electrode. And make sure that these are equalized going into this driver amplifier that then sets the voltage on the counter electrode in order to get the current flowing properly. So before moving on to figure out how do we actually measure the current out of this thing, I just want to point out that the structures that I showed earlier had the working electrode grounded. That's not strictly necessary. We could, it's the electrochemical cell is a 3-terminal element. We could, hook it up in a multitude of different ways and still get a system that works correctly. Here is shown one way where we have the counter electrode grounded and the cell voltage between the working electrode and the reference electrode, again, is set by some feedback circuits here. So there is one advantage of doing this. If you end up having like ground bounce or ground noise or something on your system, you probably don't want your working electrode to be grounded. Again, most systems don't have severe grounding issues, but some do. And so floating the working electrode with respect to the reference electrode may offer some advantages. However, this circuit is more complicated than that first one I showed you. We now have to rely on the matching of these resistors and so on in order to get the kind of performance that we're looking for out of this circuit. So let's talk about how we're going to measure that current. So again, we're applying a voltage, and now we need to measure the current through the electrochemical cell. So there's a few different ways that we can measure current. There's more ways than I'm indicating on this slide, but these are kind of, I suppose, some of the main ones. One is we can use a transimpedance amplifier to take that input current, convert it into a voltage, and then pass that through a voltage mode analog to digital converter. We could mirror the current, somewhere else, and maybe we could, for example, charge a capacitor. The rate at which the capacitor charges is proportional to the current, and perhaps we could periodically purge the charge on that capacitor to create a sawtooth waveform and ultimately create a relaxation oscillator whose frequency depends on the value of the current, and then we could use a time to digital converter in order to convert that into the digital domain. We could also just directly go to a current mode ADC, use a current conveyor, and so on and so forth. So let's discuss this transimpedance amplifier configuration. I would say this is the most common way to build a potentiostat circuit with a current mode readout. So the idea here is it's basically exactly what we showed earlier with that very first potentiostat, but in this case, instead of grounding the working electrode directly, we use a transimpedance amplifier, the TIA, to forces a virtual ground, right? So instead of directly grounding it, we could use feedback to enforce a virtual ground. So the working electrode is at the correct potential here, but now we have current that can flow, well, not into the input of the op-amp, but we can have now current flow across resistor Rm that will create an output voltage proportional to the flow cell current, IF, times Rm. Okay, so this is advantageous. Now, in a CMOS process, this probably wouldn't actually be ground. It would probably be VDD over 2 or something like this, but I think you get the idea. So in this case, the working electrode is not connected to true ground, and so there is a potential that we can pick up a little bit of interference if there's noise somewhere that couples in, or if we have an imperfect gain and settling and so on in our transimpedance amplifier. Now, if you characterize the input impedance of a transimpedance amplifier over all frequencies, what you'll find is that sometimes that input impedance can start to look inductive at high frequencies. This can be potentially very problematic, particularly with an electrochemical cell that is predominantly capacitive. And as I mentioned, this topology doesn't directly work in most CMOS systems that have a single supply voltage. So let's study that last point just a bit more. Let's say we want to build a glucose sensor. There's two primary different types of electrochemical glucose sensors. There's oxygen-based glucose sensors, and this requires a cell voltage that is negative, let's say minus 600 millivolts as an example. In that case, that implies that the transimpedance amplifier should go below ground. We never want to have anything below ground in a bulk CMOS chip, typically, without very special consideration. So this is not feasible. Now, in hydrogen peroxide-based glucose sensors, we need a cell voltage of plus 700 millivolts. So now this implies that if the working electrode is grounded, then the reference electrode has to now be below ground. So again, this is not something we typically would like to do. So the solution to this, if we want to implement this in CMOS, is that of course, we don't apply the reference voltage directly. We apply VDD over 2 right here, and then we apply VDD over 2 minus the reference voltage to this control amplifier. This ensures that the cell voltage, V cell, is still equal to the reference voltage. But now we can have that reference voltage be plus or minus, it doesn't matter, so long as it's less than VDD over 2. Okay, which is, I would say, usually not a huge problem because there's a lot of electrochemical cells that we'll be building that don't have super large half cell voltages. But you have to be careful about your electrode selection and so on and so forth. So this is a nice solution to implement directly in CMOS. Now, instead of putting the feedback resistor across your transimpedance amplifier, we could do something a little different. We can replace it with a capacitor. Okay, so if we replace it with a capacitor, then what's going to happen is as current goes into the input of the transimpedance amplifier, it's going to charge the output voltage, right? It's basically just going to charge that capacitor. So we can say here that V out is equal to T over 2 Cm. Cm is the integrating capacitor times IF. Okay, I suppose that's right at the peak value right here. Okay, so that's at time t over 2, right? So it's basically just a linear ramp based on the amount of current. Now you could add a capacitive DAC here to adjust the integration time. So if you have less capacitance added, you will charge more quickly. If you have more capacitance added, you're going to charge a lot slower. But basically the idea here is you charge up this capacitor. You can't do so indefinitely, otherwise the voltage will go to infinity, which is obviously not possible. So what we do is we have this additional switch, S1, that once the voltage reaches a certain amount of amplitude, or once a certain amount of time has elapsed, we briefly close this switch, which purges the charge on the integrating capacitors and allows the process to repeat again in the next cycle. Okay, so this is a nice way that we could convert this current into either a amplitude varying signal if we have a fixed integration time, or into a time varying or frequency varying signal if we fix the peak amplitude and let the time t vary with the input signal strength. Now we do have to mention that with this switch here, you do have to be careful about charge injection. You want to make sure that that doesn't corrupt your circuit outputs. So there's all sorts of other ways we could do this current measurement. In this case, we could put the resistor that converts the current into a voltage just in series with the working electrode. That's what's shown on the left over here. The downside, or I mean, the nice reason to do this is you don't need the TIA anymore, but now the cell voltage, V cell, between the working electrode and the reference electrode, now it's going to depend on the current, right? Because the current flowing through the working electrode is going to cause an IR drop across this RM. This is really our readout. And so now we need to construct this additional feedback circuit that is going to feed back into this control amplifier and to the reference electrode to make sure that our cell potential is set to the correct value. Another way to do this is instead of putting the readout resistor in series with the working electrode, we could put it in series with the counter electrode as shown on the right hand side here. So in other words, just put it between the control amplifier output and the counter electrode itself. This one actually works out quite well. In this case, the working electrode is fully grounded, or it's connected to true ground, so that's usually quite nice. And what we have to do is we have to now take a differential measurement of the voltage drop across RM in order to read out its value here. This requires a differential amplifier, in this case implemented as two buffers, followed by a differential to single-ended amplifier. So this certainly works, and it works okay. But now we have a voltage drop across RM, which, and as the current increases, this results in a decrease in the operational range of the circuit, right? So if you have too large of a voltage drop across RM, you're going to have a large, that may ultimately impact the ability for your control amplifier to operate in its linear range. So as I mentioned earlier, a potentially nice way to read out the current is actually to just use a current mirror. In this case, we are taking that original potentiostat circuit that we had right at the start and having the output of the amplifier drive a additional common source amplifier constructed through the PMOS gate M1, and then just having the same gate voltage mirrored through M2, which we can then pass through resistor RM in order to create a voltage mode output. Again, some advantages of this circuit is that the working electrode is at true ground, which is nice, hard to have ground coupling come in. We don't have very many active components in the signal path, which is nice, and as a result, this can be fairly low power. And what's nice is that we can switch RM as needed to adjust the range. I'm not sure that dynamic range is the right word here, but adjust the range. You know, if we have a large current, we can use a low RM, and if we have a small current, we can use a large RM to get the appropriate output voltage. And importantly, adjusting RM in this way doesn't affect the loop stability or dynamics at all. It's outside of the loop. Now the downsides of this is that while we have two gain stages in the loop, we have the op amp and we have the gain of the common source amplifier in M1. And importantly, the gain of this second stage amplifier M1, I mean, its transconductance depends on the current, which is ultimately, you know, dictated by the operation of the cell. And so as a result, its gain can vary quite a bit. Its transconductance will vary quite a bit, and therefore the loop gain will vary. So you do have to be very careful if you want to get this loop to stabilize. In particular, if there's a large capacitive load, this could result in a slightly unstable system. And of course, this only, again, still only works with single supply CMOS. So to address stability, we could replace that current mirror transistor as a common source amplifier with the source follower. In this case, M1 is now an NMOS instead of a PMOS. So this has less gain. This will make it much easier for the loops to stabilize. In addition, there's less dependency on transconductance to get this loop operating correctly. But do note that you have a VT drop across the gate to source, assuming that you're operating in above threshold anyways. In subthreshold, you know, you need some gate to source voltage, depending on the size of M1, in order for this to work. But again, we can still only measure negative cell voltages. So one way to get around this is, well, you could just flip the polarity of the cell, right? So instead of having the cell on the bottom, you could put the cell on the top. In this case, all of our measurements are referenced with respect to VDD. So our potential difference is at the output is going to be VDD minus something. But that's okay, you know, that's just a DC offset. We could subtract that. We can assume we get a nice clean VDD signal, so that's not a big problem. This will allow us to do measurements with the opposite polarity sensor. Now, you could keep the cell on top, but then have a current mirror go up like over here and then back down to get your output reference with respect to ground, so you don't have to do that DC offset removal. That's another possibility. Now, one interesting thing you could do, and we've actually taped out a chip in our lab that does indeed this, is that you can combine this circuit with the other circuit I showed in the previous slide and allow for a configurable cell polarity within a single design. So here's one example implementation of a circuit that was implemented by Graham Julian and colleagues. In this case, we're using a cell reference to the VDD supply up here. We have the current flowing through the cell. This is the potentiostat that's driving the appropriate reference voltage to get the cell voltage correct. The current through M1 gets mirrored through M2, which gets mirrored up through M3, and then eventually down into this circuit over here. Now this circuit is kind of interesting. When M5 is turned on, and we'll assume that it's on for the moment and M6 is off, then this current on this capacitor is going to ramp up. Okay. As it ramps up, we're going to have a feedback that goes into these comparators here. Now, if it turns out that the voltage exceeds, in this case, 3/4 VDD, which happens to be up here, then what's going to happen is this flip-flop is going to change its phase. So instead of M5 being turned on, M6 is now going to turn on. So now IF2 is not making its way to the output, and instead some IREF is discharging that capacitor. Okay. Once it hits the lower limit of 1/4 VDD, then these comparators will flip again. The flip-flop will set instead of reset, and we'll begin charging it again. All right. So in other words, what this does is that the time or the period of this operation is now dependent on VDD. It's dependent on the integrating capacitor, and it's inversely proportional to the current. Okay, that's the time between pulses, and then I guess the reset period here is inversely proportional to the reference current here. So the output of this is a circuit that takes a potentiostat, generates a current, converts this current into basically a frequency, into this ramping sawtooth kind of waveform, whose frequency depends on the amplitude of the current. Okay. Now I should say that they have these extra transistors over here. These are is an additional current mirror. You don't need this. You could have done it in the opposite polarity on the previous current mirror. There's an additional current mirror to minimize kickback noise. And what I mean by that is every time M5 and M6 switch at the output of this relaxation oscillator, then what's going to happen is this could kick back into the previous circuits through capacitive coupling and charge injection, and that might affect the values at those previous nodes, and so we definitely don't want that. What was nice about this particular paper is that the authors actually disclosed all of the sizes of all of their transistors for their transistor level implementation, which is nice because many papers don't do that. So you can take a look here if you're interested. So there are many ways that we can use a potentiostat. The basic way that we've been talking about so far is something we call constant potential amperometry. And as the name implies, we apply a constant potential and we measure what should be a constant current at the output, or at least the current will depend on the concentration of the underlying metabolite that we're measuring. So this is a pretty simple way to do things. It's very powerful. We can build glucose meters and lactate sensors and uric acid and all sorts of interesting sensors using this technique. But if we want to get more complicated electrochemically, we can do other things. We don't have to keep Vn or Vref constant. We could change it. We could do something called cyclic voltammetry, which is where you take the input voltage or this reference voltage and you ramp it up and you ramp it down. And what you'll find is you'll get some signature that is kind of very classical looking signature in electrochemistry for the cyclic voltammogram. And you'll find that the circuit or the electrochemical cell behaves differently when it's charging up versus when it's charging down. You'll get a different current profile. And you can see this, and the peaks of this profile can indicate certain pieces of information as well as the slopes and the general shape. So you could potentially get a little bit better specificity by doing cyclic voltammetry, particularly for more complicated small molecules. Now, if you can do cyclic voltammetry, then there's another technique that's basically the same thing. It's just run faster, called fast scan cyclic voltammetry, or FSCV. And this is often used for detection of neurotransmitters like dopamine and things like this. This is when you scan things very rapidly so that if your underlying process is changing quickly, for example, in neurotransmitters in the brain, then this will allow you to capture some of that temporal resolution. The last thing you could do is something called electrochemical impedance spectroscopy, or EIS. And the idea here is instead of putting in a ramp or a constant voltage, you would put in a chirp. What that means is a sinusoid whose frequency is being swept across some range. So in other words, what you're doing here is you're basically building a spectrum analyzer. You inject a sinusoid and you step it across many different frequencies. You observe the current at all of those different frequencies, and you can use that to assess what the impedance of the underlying electrochemical cell is, and this may reveal some information about something that you're trying to sense. So electrochemical impedance spectroscopy is typically read out using something called a lock-in amplifier. And basically what this is you take your sinusoidal signal and you multiply the output by that same sinusoidal signal, which is equivalent to basically just mixing it down to a baseband frequency effectively. And then you put in a fairly aggressive low-pass filter in order to get the underlying information out at that particular frequency. And typically you would do this for both an in-phase and a quadrature channel. So I just want to spend the last few minutes talking about some example case studies in which we do electrochemical analysis. This is a study where we built a system that does non-invasive dual fluid sensing of both glucose and alcohol in a single platform. The idea is that this is a temporary tattoo. So just like a kid's temporary tattoo, you would put it on your skin, or you'd peel it off the paper, put it on your skin, dab it with a bit of water, peel off the backing, and then you get this little temporary tattoo. And then we connected a little electronic module to this little tattoo. And this tattoo does two things, okay? The first thing it does is a process called iontophoresis and reverse iontophoresis. And the idea is as follows. We have two electrodes on either side, and we apply voltage between these two electrodes. This will induce a current to flow through underneath the skin. So it turns out that by passing a small and safe amount of current in just the right way, we can actually pull glucose molecules from underneath the skin in interstitial fluid to the surface of the skin, where we can then apply potential through a potentiostat through an electrode that is coated with glucose oxidase in order to do electrochemical sensing of glucose. On the other side, we can load a drug called pilocarpine. What this drug does is when it's injected into the skin, it just causes localized sweating. It turns out that pilocarpine is charged. So by loading it under the electrode and applying a current, we are electrically injecting this drug into the skin. So again, this is non-invasive. There's no needles or anything like this. It's just a temporary tattoo. But we're electrically injecting this drug into the skin, which causes localized sweating. The sweat percolates to the surface of the skin, at which point we can then do electrochemical analysis for alcohol consumption using alcohol, an alcohol enzyme. And so this is really interesting because it allows us to do analysis in two different fluids using the same device. We can measure both alcohol and sweat, which is well correlated to blood alcohol, and we can monitor glucose in interstitial fluid, which is also well correlated to blood glucose, and we can get a great readout. So we call this a wireless glucose sensing platform. You can see some of our test results here. We, of course, had to get university approval to buy beer and food and give it to study participants, which was fun. For some reason, testing always happened on Friday afternoons. I'm not sure why, but we ate, we drank, we tested, and we could see nice correlation between the output of our sensor in terms of the current coming out of the sensor here and the actual blood alcohol percentage or the blood glucose concentration. So we get a nice linear correlation there. So this is a really good sign of this kind of system working. So one direction that we're also working on is energy harvesting. It turns out that these small molecules like glucose, like lactate, are actually excellent biofuels. Okay, so we can load the same kind of enzymes that we're using to build our biosensors and use them to build a biofuel cell. as an energy harvester. And so it's a really neat demo. We can build these biofuel cells. We can hook them up to some electronics or watch or something like this. And when you put the whole system on, nothing happens. But then you go onto a stationary bike. You start working out. As soon as you start sweating, the watch turns on. It's powered from your sweat. Okay, so it's pretty cool how this is possible. And in fact, we can get some pretty darn good energy density or power density out of these devices. This is some measurement data where we were getting 1 milliwatt per square centimeter of power density. This is incredible. Okay. It turns out, and perhaps this is not surprising, that the amount of power that you get out of this biofuel cell is proportional to the underlying analyte concentration. Who would have thought, right? And so the idea here is not only do we have a source for energy harvesting, we also have a built-in sensor. So we call this a self-powered sensor. So we went ahead and built a circuit that leverages this concept. So in this case, we have our biofuel cell with a Thevenin equivalent output resistance. And the circuit works as follows. Normally, switch S1 is closed. And what that does is it charges a decoupling capacitor we call CDD, and this creates a supply voltage for our circuit. It's not a large supply voltage, it's 0.3, 0.4 volts, something like this, but it's good enough to run a very low voltage delta sigma modulated analog to digital converter, a power oscillator, and all of this other peripheral circuits. And when we're doing that, we're not consuming a whole lot of power. We're mostly actually in a sleep state when this phase is on. We're mostly in phase A over here, where we have reasonably high voltage. We're near the open circuit voltage basically of the system. And then what we do is we quickly open that switch and we turn this switch on. Okay, so the power supply from CDD is still active, but now we're taking as an input into the delta sigma modulator this voltage here. Let's call this Vx. Okay. Now, if we've set this RMPP, which stands for maximum power point, correctly, in other words, we have matched the impedance over here to the impedance of the biofuel cell, then Vx should ideally be exactly half the biofuel cell voltage through the maximum power point criteria. In this case, we'd be at operating point B, where we can go down, digitize this voltage through our delta sigma modulator, serialize it, transmit it out, and so on. And then once we're done, then we'll open the circuit back up, we'll close switch S1 back again, and the system recharges capacitor CDD. So what's cool about this is that there's no DC-DC converter required at all for this system. The entire system is running from 0.3, 0.4 volts. The circuit is fully wireless capable, and the average power consumption of the circuit was only 1 microwatt. So we went ahead and built this circuit and did a bunch of testing, and the short story is it works. Okay, so here you see a diagram of Vn plotted versus time. You can see what happens when we turn on the radio or turn on the ADC in the radio. The supply voltage droops quickly, but then it gets reconnected to the input and continues buffering up, and the supply voltage does change with the concentration. And if you take a look at the maximum power versus glucose concentration, you see we get a nice linear correlation. So this was a wireless glucose sensor that was powered by glucose. Okay, so this is just one of the many directions that are going on the research front when it comes to the integration of electrochemical sensors and integrated circuit technologies.